Okay, yeah, so thanks very much for the introduction. I'm very glad to be back and have the chance to give a talk here at this symposium. So yeah, I mean, indeed, like Kyoji is saying, somehow I was here for a year, about 5 years ago, and it was really, I think, one of the best years in my life somehow. I mean, on the one hand, IPMU was just really a great place to work. There were lots of wonderful people. The staff was really good at taking away the kind of practical duties so one could concentrate on work. And then at the same time, there were a lot of really great things in my personal life too. So our first daughter was born, I got married, and so on. And in fact, I remember that after we got married, the staff made us a little cake. So they had this cake with 2 flags on it, and there was a little ceremony where Kyoji played the violin and so on. So it was all it felt like a family kind of. And yeah, it was just a great time. Okay, so sorry for the somewhat unwieldy title. So what I want to talk about is, it's a math talk. Kyoji kind of said that I work in algebraic geometry. So it's a particular branch of geometry. The special kind of thing that we do is that, different from other kinds of geometers, maybe we look at objects with singularities quite a lot. And so what I thought I would do is tell you a bit about the question that involves singularities and kind of what happens near singularities. So one thing we're interested in is, if you have an object with singularities, what happens at the points where the singularities are? If I was talking in front of mathematicians, well, mathematicians want to know, what are you doing and how are you doing it? I'm not going to be talking about how I'm doing it. So my goal is just kind of give you an idea of the kind of question, so that if things go well, maybe at the end you can appreciate what the answer to the question is. Okay, so I thought I would first give a little bit of background, just what these objects with singularities are. So the technical name for them is complex spaces. This complex here doesn't mean complicated, it means complex as in complex numbers. Okay, oh, it's moving, nice. Cool, this actually works. All right, yeah, so the kind of setup is this C is the complex number, so I'm going to look at the complex numbers, d-dimensional space over the complex numbers. So on that space you have d coordinates, and I call these coordinates z1, z2 up to zd. And now what I'm interested in is near the origin in this space, I want to look at the zero set of finitely many holomorphic functions. The holomorphic function, in case you don't remember, is just a convergent power series in these variables. So for example, a special case would be polynomial. So I'm just taking, near the origin, the zero set of finitely many functions, for example, finitely many polynomials. And this kind of thing is called a complex space. So this image here is just an example. So down here you see one polynomial equation in these 3 variables, and this figure is kind of representing the zero set of this, or the solution set of this equation. These figures are never quite accurate, because the complex numbers really form a plane. So if I have 3 complex variables, it's really a 6-dimensional space. And this object is actually really a 4-dimensional thing in the 6-dimensional space, which of course you cannot plot. So the only thing you can plot is kind of what happens when z1, z2, z3 are real numbers. So these pictures is just sort of half of what the real object looks like. I allow myself one comment for the experts, which is, so this kind of thing, this common zero set, I'm calling that a complex space to keep the terminology simple. An expert would call it a germ of a complex space, because I'm only interested in what happens near the origin. Not globally, but just very close to some point. Okay, so like this picture that I drew, a typical example of this is a space that's just defined by one equation. F of these variables equal to 0. F could be a polynomial, like in the previous example, or it could be a power series with infinitely many terms. And then there's a basic fact from calculus, which we can use to, so we cannot draw the picture or anything for an arbitrary such function, but we're still interested sort of qualitatively in how does this object look like. And the basic fact from calculus is, if you go to one of the points on this so-called hypersurface, so on this set, on the solution set, if one of the partial derivatives of the equation is not equal to 0 at a point, like for example the derivative with respect to the zj variable, then what happens is that at that point you can actually solve for the variable zj, you can solve the equation for the variable zj, and the solution is going to be a power series in the other variables. And so then what this means is that at such a point, you can parameterize the solution set by these d minus 1 other variables, right? And so at such points, you actually get a so-called complex manifold of dimension d minus 1. It means that locally, you have a parameterization by d minus 1 independent variables. These are the ones there. Yeah. OK, and at least the other points, the points where all the partial derivatives are 0, and these points are called the singular points. So that's what we mean by singularities, right? The points where you don't have this kind of parameterization. In this particular case, you see the singularities are given by this system of equations, set all the partial derivatives equal to 0. So that's again a complex space, right? It's again defined by finitely many equations. And the singular points are kind of the exceptional points, the special points that we're interested in. OK. So again, just another small picture and kind of the general statement. So if I have any complex space, any one of these objects that I'm interested in, at most points you have such a local parameterization. You can actually parameterize it by independent variables locally. And these good points are called regular. And at those points you have a manifold. And then there are these other special points where you don't have a parameterization, and these are called singular points. In this picture here, again, this is just sort of a two-dimensional picture of something that's really higher dimensional. You see that the typical point, you have two independent variables that parameterize the thing. And then you have these special points where the thing sort of crosses over itself, where you don't have such a parameterization. So in this case, the singular points would be that line, and everything else would be a regular point. And that's kind of the typical behavior, OK? Now, since I'm a mathematician, I like to have a little bit of notation for this. So if X is the complex space, then I'll write X sub reg for the set of regular points, the points where you have the parameterization. And this set contains almost all the points of the space. Since we have this parameterization, this set is a complex manifold. And if you look at how many independent parameters you need to describe it at different points, that's called the dimension of the complex space. So a surface, for example, a two-dimensional thing would be something where at a typical point you need 2 parameters to describe it. And then the set of singular points, I'll write X sub sing. And I mean, in general, if you have the equations for X, you can write some pretty complicated set of equations for the singular points involving various derivatives and so on. It's a little more complicated than in the hypersurface case, but you can still do it. OK. And so now, yeah, I want to tell you kind of one of the main results about these objects, and about sort of that gives a different point of view on where the singularities come from. There's a very nice picture that this goes back to Hironaka, who proved a very famous theorem about these spaces with singularities back in the 60s and 70s. So this goes under the name of resolution of singularities. So what Hironaka discovered is that if you have a space with singularities, that you can actually always understand it as being, in some sense, the shadow of an object without singularities. So he found that every singular object, there is an object without singularities, a manifold that lives in a higher dimensional space, and your singular object is kind of the shadow of this manifold. And the singularities appear because when you take the shadow, some more stuff might be forced to cross over itself. In fact, what he gave is an actual process, an actual algorithm for how to reconstruct or how to construct one such manifold starting from the singularities. And this method is called resolution of singularities because you kind of get rid of the singularities. So you start from a complex space, and then you kind of change the singularities until you actually get until they disappear. So here's a kind of very simple schematic picture of what this thing looks like. So down here in the plane, we have this curve that has a singular point where it crosses over itself. And you can see that this curve in the plane is the shadow of a curve in 3-dimensional space. And in 3-dimensional space, the curve doesn't have any singular points. At every point, I can parameterize it by just one variable. But when I project it, the curve kind of crosses over itself, and it creates this singularity. And so this is the picture that Hironaka gave. So he said that if I have a complex space, then I can always find a complex manifold in a higher dimensional space, so that my singular thing is the shadow of this complex manifold. And so what this means is that there's a mapping from the manifold down to this complex space. This I'm calling R, this mapping. And at most points, this mapping doesn't do anything. It's just upstairs, it looks exactly like downstairs. Except at the singular points, the singularities kind of get pulled apart by this. Or conversely, what the mapping R does, it takes some points upstairs and kind of smashes them down in such a way that you create singularities. And Hironaka gives a kind of nice story in some book by him that I read. So he has this nice analogy with, like, there's this world of ideas and then the actual sort of messy real world, and you have these ideal objects, and the actual messy world is sort of the shadow of these ideal objects, and he kind of says that this is kind of like this. Okay, so these are the objects we're interested in. So spaces with singularities, and we can always realize them as shadows of manifolds. Now let's go to the actual question that I want to tell you about. So I'm calling this the extension problem. So again, let's look at the schematic picture. So let me just explain what the problem is. So these manifolds, these so-called resolutions of singularities, you can always find them in such a way that outside of the singular points, nothing happens. The space, the manifold, looks exactly like the regular points downstairs. You only change what happens at the singularities. And so then if I have some kind of object, like for example, a function or something like that, down on my complex space, on the set of regular points, then because the set of regular points down looks exactly like its preimage upstairs in this x tilde, I can take my object downstairs and transport it up to this x tilde. So for example, on this curve x, if I have some object that exists outside of the singular point, I can transport it up and get an object upstairs that exists outside of the 2 points. And then I can ask upstairs, does this object extend across these missing points? Can I actually sort of extend it or fill it in to get an object on all of x tilde? And this kind of question is the extension problem, right? So if I formulate it a little bit more precisely, I will start in general with a complex space, and then I take one of these resolutions that doesn't change the regular points, only changes what happens at the singular points. And then I give myself some object on the set of regular points, I pull it back up, and I ask, does it extend across the missing points? And specifically, I'm interested in this problem for holomorphic functions and then for these so-called holomorphic differential forms. For holomorphic functions, it's an old problem, and the solution has been known for a long time. For differential forms, not. It's quite new. Okay, so if you don't know what differential forms are, don't worry, I'll review that a little bit. Okay, let's first talk about holomorphic functions. So again, a holomorphic function is just a name for a convergent power series. So, it means that if I'm on a complex manifold, for example, I can have these local parameterizations. So I can choose these local coordinates that parameterize my manifold in maybe z1 up to zd, and I'm looking at functions that, with respect to these coordinates, can be written as convergent power series. For holomorphic functions, you can ask this question. If I have a holomorphic function on the set of regular points, I pull it up to the resolution, does it extend? And that's an important enough question that people made a definition for this. A complex space with singularities is called normal if it has this property, if holomorphic functions always extend across the singular points. This is an old notion, so if you study complex analysis, you look at textbooks about these complex spaces, you'll find chapters about this notion. So people kind of understand what this means, what it tells you about the singularities of the space, if your space has this condition. People in math always choose the names in a kind of normative way, so you choose the name in such a way that the name suggests what the good thing is, right? So you call this normal, but to sort of imply that the other ones are not good and you don't want to look at them. So anyway, a lot of things are known about normal spaces. For example, if your space is normal, then it's known that the set of singular points is pretty small. The dimension of the set of singular points is actually less than the dimension of the space by at least 2. So for example, if X is a surface that is normal, then the singularities are 0-dimensional, so they can only happen at like individual points. In the case of hypersurfaces, so things defined by one equation, this inequality is actually equivalent to normality. So we understand normal spaces pretty well. So now let me go to differential forms, which is really the thing that I'm interested in here. So holomorphic, or these differential forms, what you can think of is differential forms are like a way to do calculus on manifolds. So the point about a manifold is that you don't have preferred local coordinates. You have a way of choosing local coordinates, but there's no preferred choice. And differential forms give you a way to kind of do calculus in a coordinate-independent way. But it's something that only makes sense on manifolds. So let's say I have a manifold, a complex manifold. I choose local coordinates, Z1 up to Zn. And then each of these coordinates, I make a symbol that's called the differential of the coordinate, and that's written dz1 up to dzn. And then a holomorphic form is just a combination of these differentials where the coefficients are functions, holomorphic functions that vary from point to point. More precisely, it's called a one form. And then you can put them together in this way with these little wedge symbols. It's called the wedge product. And you can make forms of higher degree, so 2 forms or 3 forms or 4 forms. And again, it's just basically, these symbols just serve as placeholders, and it's just a bunch of functions, basically. So you can go up to n forms, I guess, n being the dimension of the space. So for example, a holomorphic n form would be, it's basically just a different name for a function, but you keep track of these symbols, d1 up to zn. And they kind of retain some information about the derivatives. And then the main point is that where you don't have a preferred choice of local coordinates, right? So what happens when you change coordinates? Say you choose, someone else chooses a different set of coordinates, maybe w up to wn. What happens? Well, these differentials, they are supposed to transform under coordinate change, kind of like by the derivatives of the coordinate change, by this kind of formula here. So it involves the derivatives of the functions. And these local expressions for the holomorphic forms, they're supposed to work in such a way that when you change the coordinates, the expression transform according to this rule. So for example, if I have a one form, like up here, and I want to see what it looks like in different coordinates, I'm supposed to replace each of the dz1, dz2, dzn by this more complicated formula involving the derivatives. And then I also substitute the w's into my functions, and then the new expression that I get should be, again, the local expression, right? So if I do differential forms, I really have this compatibility under coordinate change. Okay, so these are the things that I'm interested in here. For doing calculus, people also work with differential forms. People usually work with differential forms where the coefficients are more general functions, not holomorphic. But here I'm specifically interested in the holomorphic ones, where these coefficient functions are holomorphic. Okay, and so then here's the more precise statement of the question, so of this general extension theorem. So I will take, again, a complex space. I resolve it to get a manifold, both singularities. I resolve it to get a manifold. And then my question is, if I take one of these differential forms on the set of regular points, I pull it up to this x tilde, does it then extend over the preimage of the singular points to a holomorphic form on all of x tilde? And I'm going to assume to begin with that the space is normal. Right? Remember, normal means that this extension problem works for functions. And I'm assuming that it's normal so that I don't already run into trouble with functions. I want to concentrate on the aspect of it that's just related to differential forms. The other nice thing is that the set of singular points is kind of small, so I don't have to extend over so many points, right? Because the singular set is not so big. So that's the question. Can I extend these holomorphic forms from the set of regular points to the resolution? Yeah, okay, and so now I guess I will just tell you 2 results. So there's one older result and one newer result that basically answers the question. So, well, okay, so the good news is the question has actually already been answered back in 2011. So there was this group of these 4 people, Greb, Kebe, Koskovac, and Peter now. So they're all algebraic geometers in Germany and in the US. And they proved what was basically considered to be the final word on this question. They looked at, for technical reasons, they had to look at a slightly more specific situation. So instead of taking any complex space, they looked at an algebraic variety. So an algebraic variety means that the equations that define this x inside of its ambient space, they're not arbitrary convergent power series, but they're polynomials. These algebraic varieties, they're slightly simpler, right? Because polynomials are simpler than power series. So you can do more things with algebraic varieties. But then otherwise general setup. So you take a resolution by this complex manifold. And then what they showed is that if the singularities of the space are relatively nice in a technical sense, then this extension problem for differential forms can be solved. Then you can always extend the differential forms. Relatively nice for the singularities means, for the experts, it's a condition called KLT. Never mind what this means precisely, but the point is that this KLT condition, it doesn't come from this problem. This was a notion, a class of singularities that was studied in a completely different part of algebraic geometry called the minimal model program. So people in this minimal model program, they arrived at this notion and they had a sense that somehow this is a good class of singularities. And this theorem at the time was seen as evidence that yes, KLT singularities are a good class because this kind of theorem works for them. So they had this kind of general philosophy that somehow KLT singularities are really good. They're almost as good as not being singular at all because things like this work. Okay. Now, it sort of turned out to be useful to look at an example or a class of examples. Well, I mean, I guess I kind of gave away the conclusion, right? So the conclusion is that it was considered to be definitive. In fact, it's not quite actually the correct result. So it turns out that there's actually a different correct result. But how did we get to that point? Well, we looked at some examples. And the nice class of examples are these so-called cones. So I kind of drew a schematic picture of this. The main player in these cones is a projective space. So this thing called PD minus 1, complex projective space. So what complex projective space is just simply that you take C to the D, so complex space in D dimensions, and then you look at all the lines to the origin in that space. You get a space of dimension D minus 1, and that's the complex projective space. So every point in this PD minus 1 is actually just a line in usual affine space. Now, if I start from a complex manifold that sits inside of this projective space of dimension n minus 1, then like here, this y, this curve that sits inside of the P2, then every point of this y is a line in CD, and I can take the union of all of these lines. If I start from something n minus 1 dimensional, I will then get an n-dimensional object, the union of all of the lines. And this is called the cone over y for the obvious reason. If you look locally near the origin, this would be an example of a complex space. In fact, it's a little better. It's actually an algebraic variety. It's actually, the equations are actually defined by polynomials. And you see that this cone is basically, it's a manifold everywhere except at the origin where all the lines cross, it has a singular point. So this is a very nice test case, right? Because you just have one singular point that you need to look at. How do you resolve it? Well, so there's this unique singular point that I drew in red here where the lines cross. And the reason why it's singular is because all the lines cross. So the way you resolve it is just you separate the lines, you pull them apart. So if you do this, then you get the kind of thing like on the left. You still have all the lines, but now all the lines are separate. So on the left-hand side, this resolution is now a manifold, but in fact, it's a line bundle, right? It's something that's a union of lines. Each point in the original y now has a whole line sitting over it. And when you go from this manifold to the cone, what happens is that the 0 point in each of these lines, that's all together, that traces out another copy of y, that all gets collapsed to the singular point. So this picture is very explicit. We understand a lot about line bundles, so we can just do calculations here. We can just calculate what all the things are in this specific example. Yeah. So we can figure out when is this x normal, when do holomorphic functions extend, when does it have this KLT property for the singularities, when do holomorphic forms extend, and so on. We can just calculate everything in terms of the original y. And the conclusion from this example is rather surprising. It turns out that you don't actually need any kind of assumption on the singularities. So what happens in this example is, if your space is normal, and if the n forms extend, n being the dimension of the space, then actually all the forms for all the other values also extend. You don't need this extra condition on singularities like KLT. Okay, so if you assume normality, remember, means that functions extend. So what it says is, in plain English, if functions extend, which is kind of at one end, and if the n-forms extend, which is at the opposite end of the range, then everything in between also works. You just have to test the two cases at the end. Well, okay, and then if you're optimistic, so everyone believed that cones are kind of the representative example, so then the cones tell you what the correct result should be, right? There shouldn't be any condition on the singularities. And in fact, that's what we showed. So the actual optimal theorem is this one, which I proved together with Kebekus when I was in Germany this summer. It just says exactly as in the case of cones. So if for any space, not a cone, any complex space, if it's normal, so if the functions extend, and if the n-forms extend, then everything in between also extends. So this is actually the correct result. Maybe I can say that as a sort of general philosophical point, people in algebraic geometry already realized in many other cases that the behavior of these n-forms kind of governs what happens for the other forms to some extent. So this kind of shows this principle. Now, surprisingly, the people who wrote the other paper back in 2011, they actually mentioned the principle in the introduction. So they say in the introduction of their paper, we have this general principle that n-forms govern everything else. But then they didn't somehow live up to the principle. So this is the correct result. OK, so thank you very much.